does 2 come from? And I'm like, oh. So we forget to bring it around.
That's disappointing.
I know, right? Like, I just completely missed it. That I'm like, oh, I didn't pay attention to that. No, that's just me being not
Okay. So let me just say a word or two about the quiz. I have put the solution on Blackboard, as usual. Then I'll just say a word or two about problem set. The quiz, 2, I guess, points to take away in terms of things that I saw in your answers. 1, the Boltzmann factor, very important to remember that negative sign in the argument of the exponential. It's very important. Okay? So you have to watch out for that, and every time you write the Boltzmann factor, it's e to the minus beta times the energy of the state. Now, the energy of the state, depending upon the system, could be positive, could be negative, could be 0. Right? But it's e to the minus beta times the energy. Okay? So in the first part of the first question of the quiz, you just had to write down that the partition function z is the sum over the states of the Boltzmann factor for each state, e to the minus beta times the energy of the state. Second question was that the probability that you'll find the system in a particular state, P of S, is the Boltzmann factor for that state divided by the partition function. So e to the minus beta energy of state S over z. Okay. Then I gave you a toy system with 4 microstates and a particular energy level scheme. And I asked you to write down the expression for the partition function for such a system and simplify it. And so what you get for this 4-level system, you can see from the energy level diagram that states S2 and S3 are degenerate in terms of energy, at the same energy. But the partition function is the sum over states, so we'll sum over all 4 of the S values, e to the minus beta times the energy of state S, so you'll have 4 terms, right? So this will be e to the minus beta epsilon 1, that means epsilon of S1, plus e to the minus beta epsilon of S2, plus e to the minus beta epsilon of S3, plus e to the minus beta epsilon of S4. These 2, of course, are exactly the same, because state S2 and state S3 have the same energy. And the energy of state S1 happens to be 0. So this first Boltzmann factor just becomes a 1. And then these 2 are the same, so let's just write this as 2 times e to the minus beta times the energy of that state, which happens to be 0.1 electron volts. And then the last term is e to the minus beta times the energy of state S4, which is 0.2 electron volts. Then all I did was write in that beta is 1 over Boltzmann's constant times the temperature. I gave you the value of Boltzmann's constant in units of eV per Kelvin. And I got the expression for the partition function to look like this. 1 plus 2 times e to the minus 1,160 Kelvin over the temperature in Kelvin, plus e to the minus 2,320 Kelvin over the temperature. Okay. That's what I got. Then I asked you to look at the limiting behavior of this for extremes of temperature. Like what if the temperature of the reservoir is approaching 0 on the Kelvin scale? What is the partition function reduced to? Right? So you got zeros are approaching the limit of 0 downstairs. So these are arguments, these exponentials are becoming e to the minus infinity, which is 0. So those 2 terms go away and you just have the 1. Only the ground state remains, and its energy was 0, so the Boltzmann factor for that is 1. Now in the high temperature limit, T going to infinity, you've got an infinity downstairs, or you're approaching the limit of an infinity downstairs in the argument of the exponential. So this is approaching, each of these is approaching e to the 0, which is 1 for the exponentials. So you just get 1 plus 2 plus 1, 4 states. Okay? High temperature limit, you just add up the number of states. Okay? 4. Then I asked you, suppose the temperature of the reservoir is 1000 Kelvin. What's the probability of finding the system with energy, epsilon of 0.1 electron volts? Well, what you calculate with the probability, P, is the probability of finding the system with a particular state, S, where the Boltzmann factor depends on the energy of that state. I'm not quite asking that. I didn't ask what's the probability that you'll find the system in a particular state. I asked what's the probability that you'll find it with a particular energy. And the energy I picked is 0.1 electron volts, which happens to be the energy for which there are 2 states. So you've got to take all the states that have that energy, well, 2 of them. So you'll have e to the minus beta epsilon of S2 over C plus e to the minus beta epsilon of S3 over C. Because you've got 2 states that have that energy. Okay? And so when I accounted for the fact that that energy has 2 states associated with it, so I shouldn't put a comma there. Okay, now I'm on to a probability of a particular energy, not a state. Okay? So the probability that the energy is 0.1 electron volts, well, you can still plug in the energy here, and of course beta is 1 over kBT, you plug in kB, and the T I gave you was 1000 Kelvin. So I got the probability look like this, intermediate anyways, over C, which at this temperature is that. So plug in T equals 1000 Kelvin. And I get 368, 0.363. Okay, so that's the quiz, and one of the key things I want you to take away from it, negative sign in the Boltzmann factor, and read carefully when it asks about probability. Does it ask for the probability of finding the system in a particular state or with a particular energy? Okay, so you can see the solution for that. And then, as far as the homework, I've also posted that solution, so you can check that out. Generally, there weren't really any big issues with the homework. There were maybe just a few cases where I wanted to see a little more detail in your work. Okay? So you can check the solution. And you're working on the next problem set, and we won't have a quiz on Thursday, so just have it. Okay? All right. Any questions on anything I've said? Okay, I want to try to get us as efficiently, quickly as I can back to where we were at the end of class before the quiz on Thursday. We were almost done studying the 2s plus 1 state paramagnet. And we found the key thing is the partition function. All right? We've got, in essence, n dipoles that make up this paramagnet. Each dipole has a total spin quantum number capital S, where capital S can be any integer multiple of 1/2, turns out. And we found the partition function for one of those dipoles out of the n. And that's the expression right there, I've written that down. Remember, pretty much everything follows from the partition function. where I remind you, of course, beta is 1 over kBt, and remember alpha was just shorthand for 2 times the Bohr magneton times the magnitude of the external magnetic field that we have immersed this paramagnet in. Okay. And then we went about calculating things like the probability of finding a given dipole in any one of the 2s plus 1 energy levels that you have when you immerse this paramagnet in the external field. Okay. And we calculated the average energy of one dipole, multiplied that by n to get the total energy, capital U, and we plotted that versus dimensionless temperature for different values of the quantum number capital S. Look like that. Okay. It's a function of temperature, where at the low temperature end, all the dipoles saturate into the ground state. We worked out what that would look like on this graph on that low temperature limit. You'll see that this particular dimensionless y-axis, what you end up getting at the low temperature limit is just the value of capital S. And we talked about why that made sense. Okay, I think that's where I left off before the quiz. And there's one more thing I want to calculate out of this 2s plus 1 state paramagnet. Since we've worked so hard on it, we might as well get as much as we can out of it. What is the so-called magnetization of the paramagnet as a function of temperature? Okay. So the last thing I want to talk about is the magnetization of the paramagnet. So what I'm going to do is find the average magnetic dipole moment for each dipole, it's a function of temperature, and then multiply by n, since there are n dipoles. So, what is the average magnetic dipole moment of a single dipole? Since we're finding the average value, I'll write that mu with a bar on top. And we find this, the way we would find the average value of any quantity, we'll sum over the states. The value of the quantity being averaged for that state, this would be mu, times the probability of that state. Okay? So we're labeling the states by the quantum number m sub s, remember? And that can range between negative capital S to positive capital S in integer steps. So that's how we're going to sum over the states. That will get us to sum over the 2s plus 1 states. We'll take the value of the magnetic dipole moment for each state, whoops, m sub s, times the probability. What's that?
No, I forgot my eraser.
Oh. The probability for the state m sub s. That's how you find the average of anything. And so what that looks like here is some m sub s going from minus capital S to capital S of the magnetic dipole moment for a particular value of m sub s. And in the canonical formalism, the probability of finding a particular state is the Boltzmann factor for that state over the partition function. Okay, now let's see, I'm just going to tell you some things because I already set some of this stuff up when I talked about this last week. Okay? So the average magnetic dipole moment of any one of these dipoles will be, okay, I'm going to bring the 1 over z out front because that's completely independent of this sum. Then I'll have to sum over the quantum number m sub s from minus s to s. Okay, what is the magnetic dipole moment as a function of m sub s? I will just tell you. You will find it in your notes from last week. Negative 2 times the Bohr magneton times the value of the quantum number m sub s. That's mu for a particular value of m sub s. And then all I have left multiplying this is the Boltzmann factor. E to the minus beta times the energy for a state m sub s. And we already worked that out last week too, so I'm just going to write that out. It's going to be e to the minus beta alpha times m sub s. Okay? So this is the sum we need to do, and then just divide by this partition function to get the average dipole, magnetic dipole moment. Okay, so the next thing I did was I multiplied and divided by a factor of the magnetic field strength, big capital B. So up front, I've got 1 over z times the magnetic field strength, sum over the quantum number m sub s. And then what I have is, I'll bring the negative out front, 2 mu sub b times m sub s, e to the minus beta alpha m sub s. I just multiplied and divided by a factor of the magnetic field strength. Now, what is this? Well, this is negative 1 over z times b, sum over the quantum number m sub s from negative s to s. 2 mu b times b is my constant alpha. So this is alpha times m sub s, e to the minus beta alpha m sub s. I'm trying to get as much similarity in structure between the argument of the Boltzmann factor and the stuff down here. These are almost the same, except for a beta. And the reason I wanted to look that way is because, of course, I've got to figure out what this sum is. Okay? Without this there, remember the sum is just a finite geometric series. If this is just a 1 here, this is just a finite geometric series, and we've figured out what that sum is. But now I've got this factor here with the m sub s, and I'm summing over m sub s. So this right here is not a finite geometric series anymore. Yet I've got to do that sum, and I want, if there is one, I want to know the closed analytic form for it. Writing it this way so that this is as close as I can get to being like this argument up here is useful, because now there's a trick for doing that sum. Okay? This is a pretty common trick in statistical mechanics. And the trick is to notice that the argument of the sum is, or can be written as, negative partial with respect to beta of the Boltzmann factor. Let's look at that. Okay? If I were to just say, do this derivative for me, you could do it. Take the partial with respect to beta of this. Well, it's an exponential, so the derivative is going to be the exponential back again, times the derivative of the argument up here with respect to beta. But the derivative of this argument with respect to beta is negative alpha ms. Which is exactly what I have downstairs here, except for the negative. Or if you want, you can take that negative and take it in there. Okay? So, what we have, you noticing that trick, is the following expression for mu average. Okay? 1 over zb, sum over m sub s, of partial with respect to beta of e to the negative beta alpha ms. Now the next part of the calculation is to note that this derivative can be brought outside this sum. It's a finite series. Right? Sum of derivatives is the derivative of the sum. Okay? So this is 1 over zb partial with respect to beta of sum over m sub s e to the negative beta alpha ms. But everything in the parentheses is just the partition function. That's how we calculated Z, the partition function. So, this is really 1 over Z times B times the partial with respect to beta of Z. Remember, everything follows from the partition function. Okay? Now the next step is just a kind of a little bit of clever manipulation. You could at this point, and this would be perfectly acceptable, I guess you would call it the brute force approach. You could say, okay, he's got the expression for the partition function up there. Take that partial, take partial of Z with respect to beta. There's the Z. See what you get. Divide by Z and divide by B. But that turns out to be unnecessary extra work. Let me show you. You can use the result we've already figured out for the total energy. Because now I'm going to write this as, I'm going to bring in the negative signs again. I'm writing that expression like that, right? It's exactly the same expression. Exactly the same. Why do that? Because the quantity in the parentheses is the average energy of the dipole. Okay? This quantity in the parentheses right here is E1 average, the thermal average energy of a single dipole. So I've reduced this down to E1 average over the magnetic field strength. That's the average magnetic dipole moment of a single dipole. So to get what's called the magnetization is you just multiply the average magnetic dipole moment of a dipole by the number of dipoles in. That's the magnetization. So this would be the total average magnetization. Symbol, big M. Take the average magnetic dipole moment of a single dipole and multiply by the number of dipoles. Well, there's my expression, right, for the average magnetic dipole moment of a single dipole. Negative E1 average over the magnetic field. So this is going to be negative N times E1 average over the magnetic field. But this is the average energy of one dipole multiplied by the number of dipoles. That's the total energy of the paramagnet, which we use the symbol capital U. So this is negative capital U over the magnetic field strength. And I already calculated the total energy. See the equation from last week in this section that we numbered equation 4. For the total internal energy. And just substitute that, see? So you don't have to actually redo any calculations. You've already used your answer for this. And so when you do that, I'll just write down the expression you get for the magnetization. 2n mu b out front, bracket. S plus a half. These hyperbolic cotangents, cough, of S plus a half beta alpha minus 1/2 cough beta alpha over 2. This is equation 5. So there's the magnetization as a function of two things, actually. Temperature in the beta and magnetic field strength in the alpha. So what I'm going to plot for you to do this with dimensionless axes is I'll divide the magnetization by 2n mu b. That'll be a dimensionless quantity. And I'll plot that versus kBt over mu sub b times b. Okay? And it's just in essence going to be the negative of that. Okay? Magnetization of dimensionless on the y-axis and dimensionless temperature on the x-axis. So just think of going out this way, the temperature is increasing. And so down here you're approaching zero temperature, you're in the ground state. They're all lined up then, the dipoles, in the lowest energy state. Okay? And you can work out that you would expect to get from that there, that you would get just the value of S. Okay? 1/2, or 1, or 3/2, depending upon what the value of that quantum number is. Then as the temperature goes up, well, you start to get more equally spread out amongst the 2s plus 1 energy levels, which tends to give you an average approaching magnetization, average value approaching 0. Because you have just as many positive M's as negative M's. Okay? Now, let me show you one other thing you can get out of this wonderful result. Right? That is, you can get Curie's law, the high temperature limit out of this. Let me show you the trick for that. So the high temperature behavior equation 5. What do we mean by high temperature? Well, of course we mean capital T is big, but let's be more specific than that. Big compared to what? Okay? Here's what we mean when we say high temperature for the paramagnet problem. We mean the dimensionless ratio that I've been using on my graphs for the temperature, kBt over mu b times b, right, is much, much larger than 1. That is specifically what I mean when I say the temperature is high when I'm talking about the paramagnet. So if that's what I mean, of course that's equivalent to saying this. 1 over kBt, well, kBt is 1 over beta, so I'm going to put a beta downstairs. And mu sub b times b is almost my constant alpha, right, except for a 2. But this is an inequality, so I can say that that has to be true as well. If that's much, much larger than 1, then kBt over 2 mu b is much, much larger than 1. Right? So saying this is equivalent to saying this, is what I'm arguing. And saying that is equivalent to saying beta times alpha is much, much less than 1. Flip it. Okay? So to say I'm in the high temperature limit of the paramagnet means that this combination, beta times alpha, is small compared to 1. Why do I want to think of it that way? Because I want to go up into equation 5 and see how it simplifies. And equation 5, the most important part of equation 5 is the combination beta times alpha. So I want to know what limit I am for beta times alpha. I'm in the small limit. High temperatures means beta times alpha is small. And then I ask how equation 5 simplifies when beta times alpha is small compared to 1. Okay? Well, the beta and times alpha, they're in arguments of a hyperbolic cotangent. So I need to know how that behaves when its argument is small. So you just look up the Taylor series for cough. Now it turns out, you'll see in a moment, I need the first 2 terms. Okay? So, cough of x is approximately 1 over x, it's not a standard Taylor series, 1 over x plus the next term is x over 3 much, much less than 1. So in light of using that expansion, how does equation 5 simplify? Okay? That's not an obvious expansion, yes? But we'll take it, right? You could go to Mathematica and it'll say, yep, that's it. Okay? Okay, so in light of that expansion for cough, let's see how equation 5 simplifies. So we're finding the magnetization in the high temperature limit. So M is approximately, remember this is for high temperatures. Well, of course we've got the 2 NUB out front. And then we've got a factor capital S plus a half times cough of a blob. For the first cough, the X that I'm referring to down here is all of that stuff. S plus a half times beta times alpha. So I need 1 over X plus X over 3. Okay, so 1 over X plus X over 3. Okay, that's the first cough term. Then minus a half times the second cough term. Now that's cough of the X is now just beta alpha over 2. So 1 over X is 2 over beta alpha plus X over 3 becomes beta alpha over 6. And now, of course, I look to simplify this. And I see, for example, that this S plus a half gets distributed through this set of parentheses. And when it does, it'll cancel this S plus a half downstairs. So this first term will just be 1 over beta alpha. But then when I go over here to this one and I take the 1/2 through, the 1/2 and the 2 cancel, I've got a negative 1 over beta alpha. So that term and that term cancel. Which is why I needed the first 2 terms. I needed the leading term in the expansion and the next one after that. Okay? Because the leading term, I had 2 parts there, and leading terms in both of them ended up canceling. So now what I'm left with, 2NUB. Well, for the first term, I have S plus a half quantity squared, beta alpha over 3, and then minus beta alpha over 12. Okay? Now, you'll probably see what we're going to do next. We're going to do some factoring. Factor the beta alpha, that's common. And either factor a 3, for example, from the denominator, or another approach is to get a common denominator of 12 by putting a 4 up here. So you can simplify that, so you can see where this is going to go. I'm not going to go through all these steps. I'm going to write down what you get when you get it about as pretty as you can. Okay? While I'm at it, remember, beta is 1 over kBt, as always. And alpha is 2 times mu sub b times capital B. So when I put all that together and simplify as much as I can, here's what I get for the high temperature magnetization. NUB squared times 4 times S plus a half squared minus 1 times capital B all over 3 kBt. And I see that the magnetization goes like 1 over the temperature in the high temperature limit. This is known as Curing's law. Okay? It's valid when kBt is much, much larger, which is an amount of energy, than the magnetic energy, mu sub B times B. That's equation 6. And now you can plot that. So that's what I did. I plotted big, just like before, big N, big M over 2N mu B versus kBt over mu sub B times capital B. And in fact, what I did is I plotted it right on top of these plots for the magnetization, which are valid for any temperature, okay, to see, right, that at high temperatures, the approximate form, equation 6, which is the dashed curves, right, the dashed curves do a good job matching up with the exact result as you go to high temperatures. Okay? So the dashed curves are equation 6, which show that the magnetization goes like 1 over the temperature. That's famous Curie's law. Okay, so that's the 2s plus 1 state paramagnet. We have studied it completely. So now, let's just keep applying the canonical formalism. Let's look at something else. Something that we didn't do, let's try, something that we didn't do earlier. We did the 2-state paramagnet earlier. Now we've done the 2s plus 1 state. Let's go back to an ideal gas. You say, but we did that in chapter 3. Well, we did the monatomic ideal gas. We worked out the multiplicity function and the entropy function for a monatomic ideal gas, where the only degrees of freedom are from translation of the atoms zipping around inside the container. Okay? But of course we know that, say, air in a room, if we want to model as an ideal gas, consists mostly of diatomic molecules. So let's start thinking about how we might deal with more complicated gases, besides just monatomic. Okay? And we're going to study the ideal gas more in the canonical formalism. But before we do the even more detailed approach, we're going to just kind of peel off part of what happens in an ideal gas with diatomic molecules, namely the molecules rotate. Remember we talked about that. The molecules rotate. Let's apply the canonical formalism, find the partition function associated with the energy that goes with that rotation, and then find the average energy associated with rotation as a function of temperature. Okay? So, next big section, let's see, where are we on our Roman numerals? I want to make sure I haven't gotten them off sequence. There'll be some pages back, right, when we start the 2s plus 1 state paramagnet.
I think we're on 6.
We're on 6. Okay, so my notes are right there. 6. Okay? Rotation of diatomic molecules. Let's study that. Now, I'm going to look at specifically a system of dilute diatomic molecules composed of different atomic species. Okay? So an example, even though it may not be the most common gas, diatomic gas, certainly it isn't, is the molecule CO, i.e. carbon monoxide. Okay? And there's some reason why I'm not saying, why aren't you worried about nitrogen or oxygen? There's a complication we'll mention a little later why I'm not jumping right into that. Okay? But I want two different atomic species bonded together to make a diatomic molecule. Okay? And of course, dilute is code for all those molecules are non-interacting. right? That's what dilute is code for, non-interacting molecules. Okay, we're going to focus on the rotation of the diatomic molecules. Okay? So, what is the rotational kinetic energy? Well, you know, the picture would be something like this. There's one atomic species, I'll draw it in a certain color, and then another atomic species, and there may be a different kind of extent to their wave function, so I'll draw them with different sizes, and with a bond between them. That's what the line means. The bond is going to have a pretty stiff spring constant, so I'm not going to worry about vibration. Right? They're not getting closer or farther away from each other. That would be vibration. Instead, this kind of dumbbell-shaped, but asymmetric dumbbell-shaped molecule is just going to rotate about its center of mass. Maybe the center of mass is there. Okay? So there's the center of mass. We are not worried about the motion of, the translational motion of the whole molecule, i.e. the whole center of mass moving through space. We're ignoring that now. Okay? So we're just looking at rotation about the center of mass, and we've got two perpendicular axes about which it can rotate. Yes? One going straight up and down, one, if you like, coming out of the board. So we can rotate about the vertical axis, given the way I've drawn this, so it would go like that. Or it can rotate about the axis coming straight out of the board. That would mean it would look like an odd propeller of an airplane that you were looking at from the front. Right? And those are the two perpendicular independent axes that it can rotate about. Okay? To do the canonical formalism, of course, we have to calculate the partition function. That means we've got to sum over the states, the Boltzmann factor for each state. The Boltzmann factor depends on the temperature of the reservoir. This is in a reservoir that at some temperature T. And on the energy, rotational energy of each state. So we've got to be able to figure out what the rotational energies are. Now this is quantum mechanics, because obviously this is a molecule. Okay? So we have to remember what we know about angular momentum in quantum mechanics. Okay? Alright, so the angular momentum of a molecule. I'm going to use the notation your book does. It is pretty common in physics when you're not talking about spin, and you might think that this would be spin, but do not call this spin. Anybody see why you wouldn't want to call this spin? Spin in quantum mechanics means what? Well, spin, remember, in quantum mechanics is that intrinsic angular momentum that fundamental particles have, like electrons, protons, neutrons, and things made out of them. So when you say spin in quantum mechanics, you do not mean something that you can see with equipment, i.e. your eyes, actually doing this, right? You can't see this kind of stuff when you're talking about spin. Okay? This is more like, well, rotation. Don't call it spin. Even though in classical physics, you would be fine to call this spin. And some people would call that spin, yes? But we don't want to call it that in quantum mechanics. I'm not talking about the intrinsic angular momentum that an electron or a proton or a neutron has. I'm talking about the angular momentum associated with this thing going around like this, or like this. Okay? So we're going to use the symbol your book does for this angular momentum, vector, capital J. And the rotational kinetic energy of the molecule, E-R-O-T for rotational, that just turns out to be, and I'll show you where this comes, well, I'll give you an argument for why this makes sense. It's the magnitude of the angular momentum due to the rotation squared over 2 times the moment of inertia. And I'm assuming the moment of inertia is the same about these two axes. Okay? because they both pass through the center of mass, and they're both perpendicular to the bond. Okay? Now, where did this come from? Right? So let me make sure everybody understands the I is the moment of inertia of the molecule. Okay? Where did that come from? Just a little tiny, tiny, tiny aside. I can argue for you in terms of physics 110, yes? Classical physics, all right? Something you saw in physics 110 when we studied angular momentum. We learned in intro physics, so a little teeny tiny aside. In classical physics, we learned that the angular momentum, we call the symbol capital L in classical physics, is the moment of inertia times the angular velocity. And we learned that rotational kinetic energy is 1/2 times the moment of inertia times the angular velocity squared. All you do is combine those two, and you see that you can write the kinetic energy due to angular momentum as L squared over 2I. Just like you can write the kinetic energy of translation as P squared over 2M. Okay? So that's the same thinking to write the rotational inertia. And why do I want to write it this way in terms of the angular momentum squared? Because there's very well understood behavior of angular momentum in quantum mechanics. Okay? Because that's the next thing. And this is important. So we put a star by this. In quantum mechanics, the values of the magnitude of the angular momentum squared, no matter what kind of angular momentum it is. Spin is a kind of angular momentum. This rotation is a kind of angular momentum, no matter what kind of angular momentum it is. The magnitude squared, the values of the magnitude squared of the angular momentum are quantized. And in fact, the allowed values of the magnitude of an angular momentum squared are, well, I'm going to have a quantum number. We're going to use little j. They are little j times little j plus 1 times h bar squared, where little j is a quantum number that has the following possible values: 0, 1, 2, ... And you can think of little j as the angular momentum quantum number. Okay, with that key result from quantum mechanics, we can say that the rotational kinetic energy of our diatomic molecule is also quantized, because it depends on magnitude of j squared. So let's write down the possible values for the rotational energy. Okay? So E rotational is the magnitude of the angular momentum squared over 2 times the moment of inertia. But the values of the magnitude of the angular momentum squared are given by this expression in terms of this new quantum number, little j. So this is little j times little j plus 1 times h bar squared all over 2I, where little j can be 0, 1, 2, ... Note there's no end to this sequence. No end. Goes on forever, in principle. Then all we do, this next part is just for convenience. Let's define an amount of energy, epsilon. It's going to be a quantity with dimensions of energy. And we're going to define it to be h bar squared over 2 times the moment of inertia. You can check for yourself that that has dimensions of energy. If we just make that definition it allows us to write the rotational energy in a somewhat compact form, little j times little j plus 1 times that quantum epsilon. Then, if you study the rotation of a diatomic molecule like carbon monoxide, one key thing you'll want to know is how big this quantum is, epsilon, because that's going to determine, basically, it's going to be important for determining the spacing of the rotational energy levels. Well, this quantum epsilon depends on the moment of inertia of the molecule, so that's going to be different for different molecules. So that's just got to be measured. Okay? So you have to measure this energy. The way you do it, or one way you do it, is you discover that, well, you give yourself a nice dilute gas. Okay? You bombard the gas with, it turns out, microwaves. You slowly vary the frequency of the microwaves. You put a spectrometer on the other side, right, to see what energy gets absorbed by the molecule. And you find that for certain frequencies of the microwaves, the molecules absorb more. Okay? You do absorption spectroscopy. And you can measure, for example, the lowest frequency for which you discover you get absorption is when you would induce with the microwaves a transition from the j equals 0 rotational state, the ground state, up to the j equals 1, first excited rotational state. That would be the lowest frequency for which you would see absorption of energy from the microwaves. Okay? And you can discover that when a molecule makes a rotational transition from j equals 0, which you can see here corresponds to 0 for the E rot, up to j equals 1, which corresponds to 2 times epsilon for E rot, then you must have absorbed a photon energy of 2 times epsilon to make that transition happen. But then we set that equal to h times f, Planck's constant times the frequency of the microwaves. And since you know the energy at which that absorption, because you observe it, occurs, and you know what frequency microwaves were sent in when that occurred, right, then you can figure out the epsilon. And so what you find is that for CO, the quantum of energy epsilon is 0.00024 electron volts, i.e. 0.24 milli electron volts. Okay? So that gives you a sense of what this energy scale is. In electron volts, not big. Remember what the transition is to go from the ground state, electronic ground state of a hydrogen atom to the first excited state? It's about 10 electron volts. Right? To go from the ground state, electronic ground state of the hydrogen atom to the first excited state is about 10 electron volts in energy needed. So we're talking about energy scales much less than that. Right? About 3 orders of magnitude. 4 orders of magnitude. Right? That's just the energy scale. It gives you a sense of what energy scale you're talking about. Right? But the other side of that is, since this is not very big, you're going to find that more than just the ground state is occupied. Excited states are going to be occupied too. Okay, let's take our break now, and then we're going to come back, and our goal will be to write down the partition function for this. Yes?
How do we know that all the, even though there's a score of magnitude difference, is there any other way that the energy goes to something else in the rotation? Or is it just...
Yes, but you have to know about what, you have to have some feeling for what the other energy scales are for those other processes, like vibration.
Yeah.
The bond could do like this. So you have to have some way to figure out what's going to be the energy scale for that. And it turns out it's much higher for vibration. Right? Now, I'm not saying that's obvious. I'm saying there's a lot of people that do a lot of kind of puzzling out of data to sort all this out. So we're presenting to you the kind of finished version of it all. Okay? But yeah, it's a challenging problem.
But here we're assuming that the thing is not vibrating.
We're assuming it's not, because I'm telling you some physics that somebody at some point, or a group of people, had to figure out, and that is that that vibration is a much higher energy situation. Okay? Sure.